Okay, so this is a PhD work of Kaarina Matilainen, and I have stolen some slides from Martin as well, so keep with me. So this is a love story or a triangle drama of some sort, based on true or fake memories from some time ago, and perhaps some events may have been changed. So the main actors are expectation and AI REML from REML family. REML, it's either restricted, residual, or reduced. So many aliases, maximum likelihood. And then we have the MC from the Monte Carlo family. So imagine time when there were no genomic data, no large RAM memory computers, no big data hype, and test day model had been just taken to use, and so there were complex new models running wild in laboratories, and we were thinking how to tame them in these models. And with having lots of unknowns and data, it's not unlike today. We have also lots of new data and models going around. So we had some pub visits, and from there we learned that it's not that simple to write down mathematical formulas to napkins, but then we had some alternatives to how to proceed. We could turn Robin to Bayesian and use MCMC, and well, perhaps that wasn't alternative at all. Another one was to use MCMC in REML, and we had been working in our corners on this one, but then we kind of decided that it's not that good avenue after all. So at least from my side, I thought that MCMC is kind of a Gauss-Seidel with Monte Carlo noise, and we had just replaced Gauss-Seidel based iterative algorithms in breeding value evaluation with the preconditioned conjugate gradient method. So it kind of felt going backwards in a way for using MCMC in REML. So we decided to be simpler and use Monte Carlo, and then we wouldn't have any mixing problems at all. So this is a play in 3 acts, and we have the Monte Carlo meets REML, and then meets AI REML, and finally it's Monte Carlo REML beats MCMC. So I have given a spoiler. So the first is some formulas will be presented, and this part of ACT is from this paper in Journal Animal Breeding and Genetics. So we have a model, a simple one. I have simplified things from the paper, just a single trait animal model. And we have the usual assumptions of breeding values from a normal density with a numerator relationship metric A times the variance, genetic variance, and the residuals. And EM has 2 steps. The E step, the expectation step, computes expectation of the log likelihood for the complete data given the current parameter values, the variance components. And then we have the M step for maximizing the Q function with respect to the variance components. So the E step, as already mentioned, is mainly solving the mixed model equations with the current variance components. And then we have the M step where we solve the next step variances, and I have only here given for the genetic variance. There is a similar formula for the residual variance as well. And the problem with this kind of approach is that, as was already in a way hinted, is that it requires the inverse of the coefficient matrix of the mixed model equations. And here is the part of the CUU matrix, and that means that inverting a matrix, which is a difficult job and has to take the sparsity account. So that's where we need the Monte Carlo to kind of scale it to higher dimensions of problems. So how to do with an MC Monte Carlo? We looked at Garcia-Cortez paper. Robin wasn't that enthusiastic about that, but decided that we could start with this one at least and see what happens. So the basic idea is that we simulate like if we have the true model. So we have the current variance components, and then when we have the model and its assumptions, and we simulate data. Then when we simulate the data, we know what are the components. We know the breeding values, we know the residual. And then we can solve mixed model equations as if we didn't know anything about them. And then we get the breeding value estimates, and then we have the true breeding values because we have simulated those. And so we can use this estimate for the prediction error variance. We have the true breeding values, we have simulated them, and we have the estimated breeding values. And then their quadratic sum gives the prediction error variance, given those variance components that we have at this moment. So every Monte Carlo sample involves solving mixed model equations. And of course that takes time, and if we were to scale this up to many variance components, that kind of complex models, we were then thinking, first thing is that how low number of Monte Carlo samples can be used so that we get a good estimate and that all the REML works. And we used a small data example for this case, and then it has about 96 variance components to estimate. And we get these kind of results with just traditional REML with direct solving of inverse matrix. It took 56 days. And then with the Monte Carlo REML, the same 1,000 iterations took 64 hours or 20 or 7 hours, depending on how many samples were taken. Of course, one would ask, why would one bother with only taking one sample? It's only one sample. What's the use of that? And is even 20 enough for our purposes? So what happens if we do this and do the iterations is that the lower the number of samples, the more there will be variation in the EM round-to-round variance components. So there will be more Monte Carlo noise. And if we use this kind of approach where the number of MC samples is low, the typically used convergence criteria of round-to-round change, when it gets small, is no longer a very good one because we have lots of noise there. So we decided to look for another kind of convergence criteria that uses several iterations of variance components, fit a linear model there, and kind of use a prediction on what kind of convergence, what kind of number there would be, the variance component, and use that in place of the round-to-round change. So round-to-round predicted values were used. And we used that one. And it gave these kind of figures for the convergence criteria, which are a bit nicer. now. Indeed, again, as the number of samples is low, there is more kind of variation in the convergence criteria, but it's quite stable, even with one sample, the green one. Another thing to note is that the convergence criteria here has a higher value than the round-to-round convergence criteria of the exact REML. So we got some results, and they were really nice. And I'm not going to go into the results of this because I'm later going to explain how MCMC REML works. So this is end of first act. We have found that the Monte Carlo REML was quite reliable and behaving similarly as the REML. And we needed to have a new different kind of convergence criteria for it to work well, so that we could find the convergence. And the problem, of course, is that the expectation maximization of REML is a slow process, and that's why we'll go for the Monte Carlo ARML, which is the next act. So from a computational point of view, EM and ARML are very much similar, and from the Monte Carlo sampling point of view in particular, they involve the same steps. There isn't anything different. The difference comes in that the ARML requires solving mixed model equations as many times as there are number of unknown variance components. So because we are interested in complex models that have many variance components to be estimated, this has a consequence that the number of mixed model equations to be solved increases with the number of unknown variance components. And in that way the Monte Carlo ARML has more difficult job. It's computationally more challenging by round. It's not because of Monte Carlo, but it's because of the ARML itself. So still, we tested with the small, and this is with the R program, how it works. And indeed, when we have ARML, the number of iterations is much less than with an EM-REML. And when we use Monte Carlo approach in the algorithm, then again we get a lower number of iterations rounds than with the EM-REML. Now, while I was preparing this talk, I noticed that there is a slight error in the, or kind of error in the paper, that in the paper it just reports these numbers with the original convergence, round-to-round convergence criteria, but does not report numbers with the new criteria. So these two sets are not directly comparable as such, but still give the picture how things go. So how does the ARML with Monte Carlo behave? And it behaves a little bit better, it seems, than the EM-REML. The round-to-round changes are quite small, and the convergence is quite rapid, and the similar variation by sampling. But of course there is this additional penalty to having to solve mixed model equations more times. due to AI REML algorithms. So this gives a very good kind of understanding that the Monte Carlo seems to be working quite well, even with the AI REML. We didn't go further with this one, but we went to testing how the Monte Carlo EM REML works against Monte Carlo Markov-Chain Bayesian method. And we had this kind of a small data set from the Nordic dairy cattle, 3 breeds, 3 models, 3 different analyses. Test a model, 9 traits, many variance components, in total almost 2,000. And 2 implementations, one in DMU and the other one in Mix99. So comparisons between kind of a software is difficult, but they should give some kind of idea on how these work. One Monte Carlo round is about 11 kip sampling rounds. And in the end, it turns out that with DMU, it took almost 300 days to do the iterations, and for the Monte Carlo EML, it took 35 days. So quite good. How about the results? They looked similar in general, and here are the 3 worst mixing components that show the greatest differences between the 2 approaches. And here the lowest one has the largest difference in the value. And you can note that how the Monte Carlo Markov-Chain, it works well like mixing there, while the EM-REML has a steady going round-to-round values of variance components. So in conclusion, the variance components estimated by Kip Sampler and the Monte Carlo EM-REML were in quite good agreement, and the same parameters that had problems in the MCMC had the same problems with the MC-EM-REML. And in terms of computing time, the MC-EM-REML was superior. So thank you.